Hello, ladies and gentlemen. Welcome back. We will be starting Chapter 5, beginning with Section 5.1, the idea of probability and myths about randomness. At the end of this lesson, you will be able to interpret probability as a long-run relative frequency. And as usual, please try these problems after we are finished. Let's get started. All right, so 5.1, Day 1, Randomness and Probability. You can read much of this information on pages 327 to 330 in our textbook. Now, the idea of probability. So what is a random process and what is probability? Now, the definition for a random process is that a random process generates outcomes that are determined purely by chance. The definition of probability is that the probability of any outcome of a random process is a number between 0 and 1 that describes the proportion of times the outcome would occur in a very long series of trials. Now, because we're dealing with a very long series of trials, we can get very small probabilities as well as probabilities that are very close to 1. When we're dealing with probabilities that are very close to 0, beware of scientific notation on your calculator. If you see a number that is greater than 1, it is in scientific notation and it actually represents an extremely small number. The letter E is what the calculator will show for extremely small values. It means times 10, and then the number that comes after it is the exponent that would be on the times 10. Now, what is the law of large numbers? The law of large numbers says that if we observe more and more trials of any random process, the proportion of times that a specific outcome occurs approaches its probability. So this is basically the end behavior of the graph. As we complete infinitely more trials, so as the number of trials approaches infinity, the proportion of times that a specific outcome occurs approaches its probability. So outcomes can be extremely variable. The proportion of times a specific outcome occurs can be extremely variable in the short run, but over the long term, if we complete the same process over and over and over again, and I'm talking tens of thousands to millions of times, then the proportion of times that the outcome occurs will approach its probability, not just in the short run, not just 50 or 100 times. Now, we use this information to help us interpret a probability. Now remember, when you're doing an interpretation, you are not allowed to use the word itself. So you can't interpret probability using the word probability. So if we, and then identify the random process that you want to state. So if we randomly select an individual from the population many, many times, if we answer a call at a call center many times, if we roll a die many times, so if we fill in the blank many, many times, about blank percent, so identify the probability as the percent or as the proportion of, and then repeat the name of the random process, will, and then describe the outcome desired. So example 1 down here is this interpretation in context. So the probability of getting a sum of 7 when rolling 2 dice is 1/6. Interpret this value. So if we roll 2 dice many, many times, so repeatedly, about 1/6 of the rolls we get will have a sum of 7. So if you were to record the two numbers that basically the two sides that the dice show each time you roll them, and then you calculate the proportion of times those two numbers add up to 7, that will occur about 1/6 of the time. If we do this repeatedly over a very long series of rolls. Now, if you roll two dice 60 times, will you get a sum of 7 exactly 10 times? 10 out of 60 is 1/6 after all. The answer is probably not. And the reason for this is that the relative frequency will only equal 1/6 after many, many trials. 60 is not really a good number for the many description. Many, again, means thousands to tens of thousands to millions of times. All right, so in the short run, it's probably not going to match. That's why people who chase wins on scratch-off lottery tickets tend to find themselves in a hole financially. 1 out of 3.5 doesn't mean one out of every 3.5 tickets. It means that out of all the tickets printed, the proportion simplifies down to 1 out of, and then however many. will be winners. You could have a bunch of them clustered. You could have a bunch of losers clustered. It's the long run relative frequency. So be very careful. This gets a lot of people, especially when they like to gamble. All right, now, for example 3, here are 2 sets of 40 coin flips. One of these is real and the other is fake. Which is which? All right, you're going to see a question pop up if you're doing this on Edpuzzle, and I want you to answer the question, is the first one the fake or is the second one the fake? All right, you decide. All right, if you said that the second one is fake, you are correct. Most people will choose the second one as the correct one and the first one as the false one, because the first one has so many clusters of heads versus tails, even though this one seems to shake down to about 18 tails and about 22 heads. This one shakes down to about 19 tails, 21 heads. When you look at the proportions, they're pretty close to each other. This one, there seems to be almost a pattern within the tails versus heads, and that's kind of a hallmark of a fake. Randomness is lumpy. In the long run, in the short run, you're going to see, a series of heads or a series of tails that don't look like they should happen, which is why the proportion of the outcome is extremely variable in the short run. But in the long run, if you were to flip this coin tens of thousands of times, then the proportion of heads versus tails would actually would approach the 1/2 that it should. Right? But randomness is lumpy. That's why we can't trust short run probability. We can only look at long run relative frequency. Right? So real, fake. And some myths about randomness. All right, now this information can be found on pages 330 to 332. So what are some myths about randomness? Applying the law of large numbers to a small number of trials. We just talked about that. And thinking that a certain outcome is due or hot. So streakiness in sports games, that's pretty much been disproven. Assuming that an outcome is due. If a couple keeps getting pregnant in the hopes of having a boy or in the hopes of having a girl, I'm sorry, you're not going to be due for a boy or due for a girl no matter how many of the opposite sex has been born in your family. All right. There are certain situations where the probability resets every single time. Flipping a coin, the coin and the dice have no memory. So no matter what happened before, all outcomes are basically equally likely the next time around. Same thing with births. Right? So read that cartoon, that explains a little bit more. All right? Try this lesson and we'll see you in class.